In this video, we will discuss classification of cam follower mechanisms. After attending this video lecture, you will be able to classify cam follower mechanism into various types. You will be able to identify and understand different types of cam follower mechanisms. You will be able to know the applications and uses of various cam follower mechanisms. So once you are aware about cam and follower and you are able to identify it, the cam follower mechanisms can be classified into several ways depending on the type of, for example, the follower motion. So if the follower motion is concerned, the cam follower mechanism can be called as a cam follower mechanism with translating follower or rotating follower. So here in this example, the follower is translating about this shaft, and in this example, the purple follower is just translating. Another way of classification of cam follower mechanism is based on the type of cam. So if the cam is radial, cylinder, or three-dimensional, there are three types based on the cam. In this example, all three cams are radial. If it can also take the shape of a cylinder to give a path for the follower, and also if it is moving in three dimensions, it is known as a three-dimensional cam. The next classification is on the basis of joint closure. This joint means the joint between the cam and follower. So how the cam and follower are connected, whether it is force closed or form closed. So force closed means that you are applying some external force for cam and follower mechanism to be joined together. And if the shape of the cam follower is arranged in such a way that the joint is made, it is known as form closed. Then also based on the type of follower in a way that what is the shape of the follower. So it can be a mechanism with follower is curved or flat, or it is causing a rolling motion, or it is sliding motion. So this is based on the type of the motion of follower in terms of curved, flat, rolling, or sliding. Another way of classification is based on the motion constraint. So how the cam follower mechanism is constrained for its motion. So it can be a critical extreme position, or we call it CEP. That means that if you divide the motion of the cam follower mechanism into certain segments, so you just know the start and end of that segment, and this helps you in making a profile for the cam follower for the cam. Another way is to use the critical path motion. In that, you again divide the motion of the cam profile into many segments, and in this type you don't just not know the extreme positions but also know how the cam has to behave during that segment. So for example, it can move through a segment with constant velocity or with linear acceleration or something like that. So these are the two main types which will be our concern, and in this course more emphasis is given on CEP because most of the machines follow cam follower mechanisms based on critical extreme positions. So if you further divide the CEP type of cam follower mechanisms, each segment, when it is defined for the cam profile, that can be further divided into some types, like a CEP type cam follower mechanism can have a motion which is rise and fall. So rise and fall of the follower, it means. Rise means the follower is moving away from the cam, or it is rising up if it is vertical, and fall means it is coming towards the center of the cam, or it is falling. Similarly, we have rise, fall, dwell. So in this type of cam follower mechanism, the follower rises, then it falls, and then it stays at a constant radius. It doesn't move at all. So that is rise, fall, dwell. Another is rise, dwell, fall, dwell. So it's a double dwell mechanism in which within one cycle of the cam profile, there are two dwells. So based on these all classifications, we further try to see the examples of all these classifications and try to understand them more. So first type I told you was as oscillating or rotating follower. In this type, you can see this cam follower mechanism. This is a follower which is pivoted at this point. So when the cam will rotate in any of the direction, this follower will be rotating about this point. So this is a rotating follower. And this one, the second one, in this mechanism, when the cam will rotate, let's say it's omega 2 direction counterclockwise, this under the load of this spring, the follower will move towards left side. And when this diameter will increase in during this complete cycle of this cam, this follower, which is roller at the moment, will move towards the right side. So velocity of follower is to and fro in a straight line. So it's a translation motion. So we call it uh, translating follower, and this one is known as oscillating or rotating follower. So basically these two mechanisms are analogous to crank 4-bar mechanism, crank rocker mechanism, or it's a slider crank linkages. So the top one is the replica of a 4-bar mechanism, which is crank rocker, where cam is acting as a crank and this fourth link is acting as a rocker. And this one, it is acting like a slider crank 4 mechanism, in which this mechanism is slider. This portion of the mechanism is slider, the follower is sliding, and the cam is again a crank. Uh, so if I clarify it further, this is the effective length of for the same mechanism. So length number 2 is crank, length number 2. Length number 3 is not shown, but it is drawn from the center of these curves. So this is effective length 3, and the length 4 is from this point to O4. So these are the 4 bar mechanism, replica of 4-bar mechanism. Similarly, this cam follower mechanism, which has translating follower, it is a replica of effective slider crank mechanism, or if you call input as crank, we can call it crank slider than slider crank. So link number 2 again is here on the cam as crank, and link number 3 is this one, which is moving from this point to the center of the roller follower here. So this is effective link 3, and link 4 is pivoted at infinity because link number 4 is a slider motion. So this roller, when it is moving from right to left or left to right, it is acting as a slider. So basically you can see that these two mechanisms are similar to the one we already have studied as crank slider or 4-bar mechanism. Okay, so next type of classification was based on the joint closure, so the type of joint they had. So if we have a force closure type of mechanism, cam follower mechanism, it means that there is some external force applied on the joint. So uh, the mechanism which we have seen up till now, you must have observed a spring. So if you have a spring attached to the follower, so this spring is acting as a restoring force. So if the follower is moving away from the cam, the spring is pushing it towards the cam, so that follower is always in contact with the cam. So this joint is a half joint. It is also rolling and also sliding. So it is a half joint. It is giving 2 degrees of freedom. It's not 1 degree of freedom. So that's why we have 1 degree of freedom in 3 bodies, because in this cam follower mechanisms we have 3 lengths. One is the ground, one is cam, and one is follower. And cam and follower are giving us half joint, making the mechanism still 1 degree of freedom. So this spring is forcing that follower to be connected with the cam. That's why we call it force closure. So you can see that this is one effectivity of this spring. In this figure, if you see, you have a cam which is rotating, and the follower, a roller follower, it is moving up and down, so it is translating one. So if you see, at any point, the follower is falling under the action of gravity. But if I show you another figure, this one, if you observe, you try to observe the difference. I would like to know what is the difference you are observing in the two examples, and what is the reason. The hint is that it has something to do with the force enclosure. Okay, so another type of the joint closure is the firm closure. So that means that you make the geometry of the cam follower mechanism in a way that they are always connected. So this joint doesn't need any external force of gravity and spring. So the shape of the mechanism is made in a way that the cam and follower are enclosed maybe within their geometry. So this is an example of the foreclosure. So this is a cam, the orange one, or you can say the light red. And if the cam is rotating in this direction, the follower which is enclosed within the geometry will never go out of it. So we don't need any spring in it. Because of the shape of the cam, the follower will be moving in this profile. Okay, so sometimes it will move towards the center of the cam, and sometimes it will move away from it, but it will be translating in one direction because it is also a translating follower, and also it is a form closed type because the follower is enclosed within the geometry of the cam because of this groove. Okay, so we can either call it groove or it is a track for the cam, for the follower to move within. Okay, so this is how the form closed and force closed work. Uh, this is another example of form closed. What is the difference between these two? Of course, you can see that the left one has a follower which is translating. The right one is have a follower which is oscillating or rotating. So you can see that within a same cam follower mechanism, you have to define more than one things to completely classify it. So this right one is oscillating follower mechanism. It is a form closed for cam follower mechanism, and similarly, we will see that there are other ways of classification in the coming slides. Okay, so based on the shape of the follower, we can also classify our cam follow mechanisms. So we are having three examples here. The first one on the extreme left is having a circular follower, and that circular disc type follower is pivoted at another point. So when the cam rotates, this follower is rolling within this point, around this central point, and also it is coming down and up under the action of this spring. So this type of follower, because of its shape, is known as a roller follower. Also, it is a translating follower. So it's a roller translating follower, and this is another example of force close because the spring is applying a force to keep these two always in contact. This one, the middle one, has a follower with the shape of a mushroom, so we call it a mushroom follower mechanism. Again, it is translating. The third one is a flat-faced follower, so this shape of the follower has a flat face. Of course, all of these three different shapes have their own pros and cons. Uh, so if I talk about the roller follower function, this one has lower friction. You already know that when there is rolling, there is less friction, lower friction than the sliding ones. Okay, so this is the advantage. But when it has extra additional pivot point and construction involved, so we can call it it is expensive than the other two. Then we talk about the flat face, the right one. It has the advantage uh, that it has more range. So it is a very easy to make follower. Of course, it has more friction, so there will be loss of energy, and but it is easier to make. And also, cam flat-faced followers are placed where the package is small. So because of this roller shape and all this pivot thing, this distance, however, it looks smaller here, but practically it becomes very large. So flat-faced, if even I take this length smaller than this, that is still possible. So if the rise and fall is not very large, I can still this use flat faced. But with the roller face, whatever the rise and fall is, at least there has to be some distance which is equal to the radius of this roller. Okay, so this is causing some increased geometry of the mechanism. So that's why, as I've mentioned here, it is much favored for the automobile valve trains. So it's written here value, but it's valve trains. Okay, so the third one, the mushroom. If I talk about this one, it is used as a compromise on, you can call them compromise on other two, but also it has an effect because of its round shape. You can also say that it has less friction than the flat face, and also if the motion is not if the cam is not moving in a big range, then still mushroom has advantage over the flat faced. Okay, so it is a compromise on the other two. And again, if you talk about the construction of much more mushroom will be little more than flat faced, but it will be less expensive than the roller follower. So if you see, the roller followers are mostly used in production machinery. So if you have a large number of rollers with you and bearings, there will be a bearing. It will be very easier to replace, and you don't need manufacturing or machining for these two need. Okay, so this is much more easier to replace. Okay, so as I told you about the mushroom followers, here you just see a profile, but this profile basically means a very lot. It has a lot of information hidden within it. So whenever you are making a mushroom follower, we will further see that how this profile and shapes are changing the behavior of these followers. So based on the type or the basic requirement of the application, this mushroom is designed and manufactured. Okay, so based on the shape of the followers, there are three types. Again, the roller follower, the mushroom follower, and the flat follower. Another classification is based on the direction of follower motion in relation with the axis of rotation of the cam. So there are two types based on this classification. Either the cam will be radial or it will be axial. So if you see this example, if I try to depict it here, so the follower will be moving in this direction. So this axis, the vertical one, is the motion of the follower, and the radial cam, the cam is radial because it has a circular motion. So this is the radius which is increasing or decreasing. Okay, so if the follower is moving in a direction which is as same as the radial direction, so this will be with the same plane. This means that it is a radial cam. Okay, so the radial along it is in the radial direction of the cam. Okay, the second example is this one. So in this one, the axis of the cam is this one, and if you see the follower, it has the same axis. So if these axes are along the same, they are parallel, we call it axial cam. Okay, if you see this left right side example again, this is also a roller type of follower based on the shape of follower, and it is translating because the follower is moving in translation. And another thing you see is it is a form closed if this roller is entrapped within this track. And also observe that if this is not entrapped and it is just following a track and there is an option for the follower to come out, we will have to apply some force in it with some spring, maybe a torsional spring here, so which will keep this follower on this track. So this is how you can say that it is be a form closed or force closed. Okay, so just to revise again, in the radial cam, the motion of the follower will be in the radial direction of the cam. Okay, so you just observe the motion of the follower with respect to the motion of the cam. Okay, and in the axial cam type of cam follower mechanism, the axis of the cam and the motion of the follower, they will be in the same axis. So here they are sharing the same axis. But here if you see on the left side, the axes of the cam are out of the plane. Okay, so these axes are perpendicular to each other, and here these axes are parallel to each other. Okay, so this is another example of axial cam. So you can see that the axes are vertical for the cam. So if I try to draw it here, this is the axis of the cam, and also the follower is moving in the vertical axis. So these axes are parallel to each other. So that's why we call it axial cam. Okay, also you can see based on the type of the motion of the follower, it is translating follower. And also you can see that the type of follower is translating and radial. Okay, so the last basis of the cam follower mechanism was based on the type of motion constraints. So the first one is the CEP, or the critical extreme position. So I told you that for the cam profile, you divide it into many segments for its whole cycle, and for each segment, if you know the start and the end positions of this segment, then you call it CEP. And you don't know how the path within the start and end will behave, so we call it CEP. The other type is the critical path motion, and you know that how the segment will behave during the motion rather than not just the start or the end. Okay, so like you know if it is going to move with constant velocity or it is going to move with constant acceleration. Okay, so if I further talk about the types of CEP, so for considering or understanding the type of CEP profile, we can call it, we will consider this cam, radial cam follower mechanism. So what other information for this mechanism is given? The cam is radial, it is rotating around this pin, and the follower is translating. Also the follower is roller, so there is force closed because of the spring. So you can understand the cam follower mechanism based on different classifications. Okay, so first of all we have to see what is dwell. So dwell is that if the follower is not moving at all. Not moving at all means that it is not either going up, not going down. So if it is staying at this point, we will call it as a dwell period. So if the cam rotates, but the radial follower, uh, if it stays in the same line, it will be known as a dwell. Okay, so it will keep on staying here. So next option is the rise. So it is not a dwell motion, so it means that the follower has to move. It means And this is another profile, which means that there will be rise and fall. So rise and fall means that in this particular segment, there will be a rise in the follower, and then after some time, so rise means it is moving up, and sometimes it will, after some time it will fall. So this is another type of CEP. This is not complex engineering problem. This is very easier than that. So in this, what happens is that uh, the follower moves for some time and then it comes down. And how it moves up? It moves up because this cam has some radius. So if this radius increases, the follower moves up because of this half joint. And if this radius again decreases, like it is decreasing here, the cam and follower in contact will make this follower come down. Okay, so that this is how this follower will be moving up and down, and we call this type of CEP program, motion program, as rise and fall. So 12 is a motion program in which this radius remains constant. Let's see, like this portion. So in this portion, for example, there is no decrease or increase in the radius. So if the cam is contact with this area, there will be no rise or fall. It will be consequently dull. So if this radius rises, it is known as rise, and then it goes down, it is called rise fall. So segment in which there is just rise and fall, we call it rise fall segment. And it has no dwell, means that after rising, the radius continuously increases and then continuously decreases. There is no unchanged portion of the radius. If the radius will remain constant for some time, we will have an additional dwell. So but in this case, there is no dwell. Then we have another motion type program if we divide the segment into rise, fall, dwell. So what happens is that the cam profile, it moves in a way that follower rises, then it falls, and then the radius remains constant. Okay, so we call it rise, fall, dwell. So between rise and fall, there is no dwell, means that the radius starts increasing, then it suddenly starts decreasing, and then there is a portion where there is no increase or decrease in the radius. Okay, so we call it rise, fall, dwell, or RFD. Okay, so this is RFD. The next type is, we call it double dwell cam profile, and based on the CEP. That type of cam profile is in a way that first of all the cam rises, then it stays here for some time, then it falls, and then stays it here for. So the complete cycle of the cam from here to here has this four motions. Okay, so this type of cam cam profile, CEP motion, is known as rise, dwell, fall, dwell. So for example, if the cam has to rotate for 360 degrees, these 360 degrees will be divided into four segments based on the design requirements. And first segment will have rise, which follower will move up. Then there will be dwell, when the follower will remain at the same radius for some time. Then the radius will start decreasing, we will call fall. And then it will be a dwell period again, in which the radius again remains constant. So of course the first 12 and the last 12 have different radius, but the portion of the cam will remain constant. So this shape basically of the cam, which we call the profile, has to change. So this change is depicted as rise, fall, rise, dwell, fall, dwell. Okay, so based on the CEP motion program, the cam profile can have these four types of motions. Either whether it will be complete dwell, there will be rise fall, there will be rise fall dwell, or there will be rise dwell fall dwell. So depending on our design requirements, we decide which type of CEP profile we have to use. So based on the information we learned so far related to the types and classifications of cam follower mechanisms, how would you completely define the cam follower mechanism shown to you? So use the different bases and comment on what are the bases and the information you can give about this mechanism. If you have any comments or any questions, please ask. I would be more than happy to help you out. Thank you very much.